Welcome everyone, my name is Mare, and in today's video we're going to be tackling this problem. So the equations y equals x squared and y equals x create an enclosed region. We're trying to find the volume of this region when it's revolved around y equals x. So y equals x squared looks something like this, and y equals x looks something like this. And this is the region that we're going for here. And we're trying to revolve this region around the line y equals x. So if you've taken a Calculus 1 or Calculus 2 course, or Calc AB or BC if you're a high school student, you're probably familiar with revolving regions around a vertical or a horizontal axis, such as the x-axis or the y-axis, or a horizontal or vertical line. However, in this case, it is slightly different and we can't exactly utilize the same methods that we're used to. So, for example, if we have the graph y equals square root of x, and we're trying to get the volume from 0 to 4 as it's revolved around the x-axis. What we would normally do is set this distance here, square root of x, to be the radius of a circle. So square root of x is the radius. And then we're going to square that and multiply it by pi and then integrate it. So we're essentially integrating or adding up infinitely many circles here, and that will get the volume of this region. So it would look like the integral from 0 to 4 of that expression with respect to x. However, in this case, if we try to do that, it wouldn't work because we have to actually get the perpendicular distance here, the distance perpendicular to the line. And we'll have another video where we actually explain how to do this method, but in this video I will actually show you guys how to do this by rotating this graph 45 degrees, which will essentially make the line y equals x into the new x-axis, and then we will have a parabola that is also rotated that will look something like this. That is a poor drawing, but then we'll have a simple region here that we can just revolve around the x-axis like we're used to, and it'll be pretty simple. So, if you've taken a math course beyond calculus, perhaps, then you might be familiar with methods of rotating axes and equations. However, in this video, I want to take us back to pre-calculus and show you guys a couple of neat formulas that allow us to rotate these equations and make this problem a lot easier to tackle. So the equations are x equals x prime cosine theta, which is any theta that you would like, minus y prime sine theta, and the new y values will be y equals x prime sine theta plus y prime cosine theta. And in this case, our theta is 45 degrees, since the line y equals x is a 45 degree angle here, which is also pi over 4 radians, but in this video I'm just going to be using degrees. And so plugging in 45 degrees into cosine and sine both yield square root of 2 over 2, which is also equal to 1 over the square root of 2. And so plugging that into both of these equations here, we get x equals x prime over square root of 2 minus y prime over square root of 2, which is also equal to x prime minus y prime over square root of 2. Since it is the same base, we can just subtract like that. And then for y, it's very similar. We get x prime over square root of 2 plus y prime over square root of 2, which then equals x prime plus y prime over the square root of 2. And now we have these new x and y values essentially right here and right here, and we're going to plug this back into our original equation, which is y equals x squared. So we'll plug this in for x and plug this in for y, and that will give us our new parabola that is not a parabola anymore, but it's rotated 45 degrees. So we have the equation y equals x squared, and we're trying to rotate it 45 degrees. As you guys just saw, the two equations that we have are x equals x prime minus y prime over square root of 2, and y equals x prime plus y prime over square root of 2. So as I said, we're just going to plug these values here, or these equations, back into this original equation. And so y is going to be this right here. So we're going to get x plus y over square root of 2. And we don't have to keep the primes here now because we're plugging it back into the original equation. So equals x minus y over square root of 2 squared. And this is our equation here. And what we want to do now is isolate for y. However, this is quite a lengthy and tedious process, and it can definitely be done, but this video is not exactly an algebra lesson. So if some of you guys want to challenge yourselves and do it yourself and isolate for y yourself, you may do that, and you will probably have to use the quadratic formula, but in this video I will just skip to y being isolated. And so when we isolate for y, we get y equals 1 plus square root 2x plus or minus, which comes from the quadratic formula, square root of 4 square root 2x plus 1, all in the square root, all over square root of 2. And clearly you can notice that we have this plus or minus here. So when we graph this equation, it will look something like this, like this parabola. I'm not very good at drawing these, but it will look something like this, and here is the desired region. However, you can tell that this is not a function because it doesn't pass the vertical line test. And so the plus or minus essentially comes in here. And so this portion of the graph up here is the positive in the equation, and this portion down here is the negative. And so we're looking for the negative portion here because that contains the region that we would like. And so the actual equation that we will be revolving is y equals 1 plus square root 2x minus square root of 4 root 2x plus 1 all over square root of 2. And so now we just have to revolve this equation from 0 to square root of 2 and utilize a method that we're very familiar with. And so, as I said here, I'll draw a little bit of a visual so you guys remember what it looks like. So we have the entire parabola kind of looks like this, and the region with the minus is this region right here. And this is the region we're trying to revolve now around the x-axis. And so our bounds of integration will be from 0, obviously, to root 2, actually, the square root of 2. And so in the original graph, it would look like we're integrating from 0 to 1, because we have this parabola here, and we have this line here, and this is the point 1, 1. However, this distance here is actually this distance here. And this distance is the square root of 2 because you have a leg of 1 and a leg of 1, and based on Pythagorean theorem, 1 squared plus 1 squared equals c squared, and we get the square root of 2 as our distance there. So be careful to, adjust the bounds as necessary when you're doing a rotation like this. And now we just plug in this equation into here. So it's a little bit tedious to write it out, but square root 2 plus 1 over the square root of 2. And this is essentially the distance here, which we will think of as our radius of a circle. And so the area of a circle is pi r squared, so we have to square this radius and multiply it by pi. And the pi can be inside or outside of the integral because it's a constant, and this is all with respect to x. And so when you plug this into your calculator, you will get an answer of approximately 0.074048. And that is the volume of the region of the equations y equals x squared and y equals x when it is revolved around the line y equals x.